Welcome to Ask and Learn.
Okay, so the engine of a Ferrari F355 F1 sports car takes an air at 20 degrees Celsius and 1 atmosphere and compresses it adiabatically to 0.09 times the original volume. The air may be treated as an ideal gas with gamma equal to 1.4. A, draw a PV diagram for this process, and B, find the final temperature and pressure. Okay, so for this problem, you're going to use the formulas in the adiabatic section about which quantities stay constant during an adiabatic process. But first, let me start out by writing out the quantities given. So we know that V final is 0.09, V initial, I'm not going to write that comma. Okay, we know that gamma is 1.4, T initial is 20 degrees C, and P initial is 1 ATM, and our goal is to get P and V. So I might actually hold off from drawing the PV diagram until I calculate PV, although I know that it's just the volume's gonna get smaller and then the pressure is gonna get higher. So if you look in the adiabatic section, you get that you got two formulas that allow you to calculate the final pressure and temperature. So the first one, we can get the final temperature by using the formula that temperature initial, V initial to the gamma minus 1 is temperature final times volume final to the gamma minus 1 for adiabatic processes. If you rearrange this algebraically to solve for the final temperature, you get a temperature final is temperature initial times V initial over V final to the gamma minus 1. T initial is 20 degrees C. And notice I'm not even converting to kelvins, which I generally do because I'm okay with my final answer coming out to kelvins and or to degrees Celsius, and none of my calculations rely on the putting together SI units and just kind of hoping that the answer comes out in SI units. Oops, I'm going to actually write down what the initial and final volume are. Okay, so V initial, I'll just leave as V initial. V final, all right, is 0.09 V initial. And yep, so then that goes to the gamma minus 1. The V initials cancel. And so we're just kind of left with 1. And so, let me write what actually, what gamma actually is. So they tell us in the problem that it's 1.4, which is close to for a monatomic ideal gas, which I think is 1.67. Okay, great. So if you take that and you plug it into a calculator, then you get that that's 495 Celsius. So the temperature increases by quite a bit. So, but it is going to only 9. The volume is changing to be 9% of the original volume. So that is quite a bit of compression and energy that must go into that compression. Okay, great. So 2, we have another formula for similar to this to get the pressure for adiabatic processes. So that formula is P initial, V initial to the gamma equals P final, V final to the power of gamma, not gamma minus 1 anymore. And if you algebraically manipulate this, then you get P final equals P initial over times V initial over V final to the gamma power. And again, we don't have to worry about converting atmospheres to pascals because nothing relies on SI units kind of all coming together to be another SI unit. So 1 ATM multiplied by, we can do the kind of the same trick as we did here, and we can just kind of skip the middleman and know that that comes out to 1 divided by 0.09, and then now we'll take this to the full 1.4 power, not 0.4. And let's see, that calculation yields 29 ATM. Oh, yeah, 29 ATM. So 29 times atmospheric pressure. So we're creating a very high pressure, high temperature sort of situation here. And then last but not least, let's do a little PV diagram. So here's P, here's V, and then here's V final. Oh, I should make that closer to the x-axis. So here's V final, here's V initial. This kind of looks like basically 10% of this whole thing. And then this is, we can have this be 29, and then this can be 1. I'm not sure what unit these volumes in, but I guess it doesn't matter. But I'll put the units for atmospheres since we know it, which is atmospheres. And yeah, so we end up at this V final, which is very small, but a pressure which is high. And then we started out at high volume, low pressure, and it kind of has some curve to it, dictated by this equation. And is there anything else to say about this problem? Yeah, I don't think so. Oh, the temperature is increased. That's not totally evident on the PV diagram. There are the isotherms curves that kind of sort of cascade. I won't include them for clarity, but hopefully it's believable that the pressure is kind of on a higher isotherm, although it's not totally visually clear.